Does that make sense?
Yes. Oh, no, but it did make sense to begin with, so it's okay.
So it hasn't changed.
Nothing's changed.
Okay, great.
Yeah.
We'll chat.
Sounds good.
But it can't just be it can't just be like a flat constant, because you gotta think about it like,
We have a flat constant.
well, you do in like X, Y, but when you're rotating, like your R is like growing as you go out, you know? That took me so long to realize.
That weird region.
Yeah.
Yeah.
Because I sat there for like a minute and thought I had it right, but like there was one thing that just like wasn't really making sense, and it took me a very long time to realize that it was my arm was
It
wrong.
shows you put a lot of thought into it.
Using soccer, like there are different leagues, no?
All right, my friends.
Yeah, exactly.
Anything you want to chat about with these that just came back? These are probably the last normal skill checks I'm going to give you. What I'd like to do for the final, like we're supposed to have 23 skill checks. That was the goal. So skill check 21, 22, and 23. I'm just going to give you a take-home assignment. Does this sound okay? No in-class stuff. They have to be written up nicely, but it's still better than coming in here not knowing what's happening, pretending to do something, and then having to do it again anyway, right? So I don't know how I feel about this, the way this all ran this semester, but
Would you do it again?
yeah, thanks. That's good, you got an A. Would I do it again? No, I would I would do something a little different. I wouldn't do those pre-class checks at the beginning. That was just stupid.
Are you going through?
Are you factoring those into the grade?
Yeah, I mean, just like, did you do them? Does it look like you know there's a math problem there? And you get full
So you're
credit.
going back to exams.
Kind of. Maybe, we'll see.
We got lucky boys. It's all good.
Yeah. I mean, even with the exams, you get to like do corrections, right? So, with my exams.
I mean,
Is that true?
Oh, yeah. Yeah.
your DPQs like exams are not bad at all.
Those weren't bad. No, the homework sets were hellacious.
Those are pretty bad.
Those are pretty bad.
Those are pretty
Yeah, my exams are usually not challenging at all.
You're pretty low on
On the exams? That's what, because I knew you could correct them, you
That's
know?
why you couldn't read this problem.
No, you could. No, yeah. And you did. And your corrections were awesome.
Oh, yeah, that's right. No, we did have.
Yeah, I mean, I'm out of my mind, but I'm not that
I
out.
know.
I'm not like, can't remember last semester out
Last
of my
time I
mind.
did remember like writing them up super deeply for no good reason.
No, because it made me happy. That was a good reason.
The clear reminder technique.
Exactly. So I will give you that last homework set on Wednesday. I kind of want to tweak it. I'm working on it to make it, I don't know, interesting, but not like, it's not stupid. I know that sounds scary when a prof says it'll make it interesting, but I just want it to actually be worthwhile and not just doing shit to do shit. Cool. So we won't meet for a final then. I will probably just hang out in my office during finals time for consultation. I'll have a bunch of office hours next week. You're welcome to come. Almost no one here ever comes to visit me and work with me on anything. Christian, Alexander, you've come. Yes, sir.
So are the skill checks, the corrections due next week, or are they due at the end of this week?
Yeah, so that's a good question. Let's just get everything to me by next Wednesday.
Okay.
Does that sound okay? Because I'll be in on Wednesday and then I can collect it from you and yeah, that's about it. Any other questions?
Yeah. What time are you in on Wednesday? Because I have like 2 or 3 exams.
Yeah,
that
next
day.
week.
What time am I in on Wednesday?
Yeah, like,
Yeah,
yeah.
that's horrible. I mean, I'm happy to like we can connect on Tuesday too.
Okay, I'll have to see when my other exam schedules are, because there's not even, most of my classes don't even know when their exams are, so.
You're gonna be here Tuesday?
Yeah, I can come in, definitely. I might as well, since everything's kind of like due on Wednesday, I'll come in on Tuesday for sure and have office hours. Is that helpful?
Yeah.
And Monday too. I'll also have office hours on Monday. Any other questions? And then Thursday, Friday,
Oh, is
I don't know about that.
Is the math on the quad part of the skill check, or?
Yes,
Okay.
that will actually be, one of the problems on math, will be come draw it on chalk. Although the weather's looking a little grim for Friday.
What's grim?
Grim looks like a high of 54 and kind of overcast, so.
No
Okay,
snow.
I thought you meant like rainy. Just like
I mean, hopefully not. Hopefully not. If it ends up being super shitty weather, we'll just like do something. We'll figure it. We'll figure it. But I want you to come visit me. I don't want to be out there alone, like trying to stir up interest in math among people who don't give a shit. You all give a shit. So you got it. You're my like sure bet audience to be out there caring modestly about things. Hey, I understand work, kind of. It's stupid.
Yeah.
It's the dumbest
Talk
shit
about
ever.
it.
It doesn't even make sense.
Social distance.
You want to hear, tell us what you learned?
Yeah, I am good. Yeah. So if I hold this thing here, right now the only force acting on it, I guess in theory, is gravity, right? I mean, besides my hand holding it up, right? But there's like this force field. There's this vector field of gravity. And I actually wanted to do an example with this today, but if we assume the Earth is locally flat, that's a pretty good assumption, then the force of gravity is this kind of constant vector field where the forces are always acting down. So I take my little thing that has mass and I put it in here and I hold it up. There is no work being done, even though I'm exerting myself and my fabulously powerful arms to hold this thing up. That does not work. Work is motion, is basically how much you're in unison when you move things with the force field. That's a terrible definition. But so positive work is done when you move in conjunction with the force field. So positive work happens when I take this thing, I don't know why I have to pretend it's on the board. If I take this thing and I move it in unison with the force of gravity, that is positive work. So positive work means you're moving in conjunction with the forces as they be. That's like a pirate definition or something like that. Negative work is when you're moving completely opposite. And then shades of work are, so for example, if I moved it 45 degrees like this, that might be a shade of different work. But what it's going to turn out is that in certain vector fields, like gravity, they are conservative. And so what happens is it doesn't really matter how you get from point A to point B. All that matters is you did change position in the vector field. I mean, I don't understand it, so, you know, I watched some YouTube videos and tried to remember something. But yeah, so like if I take this thing and I move it from here to here, that's the same amount of work if I hold it for 20 years here, move across, and then move down. Whatever. So the legend goes. What's that?
Work only matters at the first and last point, not the middle.
Yes,
If the field is like, if there's no curl.
Yes, and we're also going to talk about that too. So, yeah, if it's just right,
Yeah.
if it's just perfect, then that is the case. Let's actually kind of refresh our memory about what this means and how to do it, and then talk about stuff like curl. And we will meet on Wednesday I might have a few last things to tell you, but I will mostly be handing out the final problem set, and then we'll take this time to work on it and clarify what needs to be clarified. But let's say I've got this force field, F, this vector field, and it depends on two variables. Let's just start there and refresh how this works. So to write this out, I would use that notation. I've got these are scalar functions, and I just slap them into the components. Or I could write it like this. And I have a range of parameter values, A to B. So this is essentially giving me at every single point in the plane whoa. This is, oh, sorry, excuse me. No, this is just, excuse me. Sorry, I got my notation screwed up. I'm moving ahead too fast. This is an F1 of XY. This is an F2 of XY. Sorry, we don't have a parameter yet. That's when we get our actual path of motion in there. So that is what could be written like this. Apologies. And that means at every point I've got a vector that depends on the coordinates of the plane. Erstwhile, so this is filling the plane with vectors representing, could be force, doesn't have to be, but probably that's the easiest interpretation. I've also got an object that I'm moving through this vector field, and it's going to start at some, well, it's defined by this function r of t that is a vector value function. Now I got the right notation. So x of t, y of t, and t has a certain range to it. This could be infinity, this could be minus infinity, but it probably won't be for us. And I'll call that C. So C is this curve that starts at R of A, whatever that coordinate is, and then ends at R of B, out here. And there's this motion that is implied by this being the start of the parameter space and this being the end. Just a really quick reminder of something we talked about. That path C, if I travel backwards on it, that's called minus C. So minus C is just moving backwards along that same path. And let's pick this up from here. So how do I actually evaluate the total amount of work done from this point to this point, moving through a vector field, which is the only way I can get work done, by moving in the vector field. And so let's put total work here, because it's a nice thing to label it to, is the line integral, and we derived this last time, f dot dr. So this is the notation of the total work done moving along this path C through the vector field F. How do you actually evaluate it? Well, you're going to take everything back to parameters. We're going to integrate from A to B for the t variable. The F, I'm going to evaluate at every point along the curve. And then this dr becomes r prime of t, so the derivative of this vector value beast, dt. Let's take this another level. This is integral a to b, f of r of t. And think about what the derivative of this is going to be. It's going to be, and again, that's a dot product, x prime of t comma y prime of t. So this derivative of the curve is just the derivative of each of these components, dt. And now this guy here, let's go back to that notation right there. this is integral a to b f1 of r of t, comma f2 r of t, dotted with that beast right there. And we're almost done. I just want to show you the multiple notations because I'm not sure what y'all see out in the wild. And now the last thing I want to write is this dot product written out. So this is going to be integral a to b f1 evaluated at r of t, dotted with that vector there, so that's times x prime of t. And I could put the dt here, but generally we don't. But I'll save it for the end. And then I've got f2. So this is f1, f2 of r of t, dot times, now it's normal multiplication, y prime of t, and then dt. Sometimes you'll see this all written just notationally. Instead of this, you might see this notation. Integral over c of f1 dx plus f2 dy, that's just notation. That means this. And if you compare this to that, I think it makes the most sense. This times dt is the dx, this times dt is the dy. But that's just notation. Has anybody seen this for line integrals in your classes? This notation here? No? No? How many folks have seen line integrals in other classes? Not many. Not many. Next semester. Next semester. You're gonna be powerful. What's that, Daniel?
You've seen them in the
We'll see in the NM next semester.
and E&M.
That makes total sense. So let's do a quick example to practice this up. That's kind of a review. We actually did the derivation last time, but we are not doing that again. So if I tell you that f is, I'm going to write this a little differently, 2x plus y I plus x minus y j. These are the component vectors, x and y. I want to take a curve C that travels along, so I'm going to be very vague and cagey here and make you do a little bit of work. Travels along the parabola y equals 1/4 x squared from 0, 0 to 2, 1. And what I want to find, is there something, you're good?
I'm just visualizing what.
Oh, gotcha. Yeah, we're gonna definitely want to draw some pictures. But what I want is this. So step one is, let's get the curve C parameterized. So take a minute, I just kind of wanted to pull some skills together today. Take a minute and come up with a parameterization for C first. It's a little bit tricky. You gotta pull some things, you gotta move backwards and then forwards. And let me get a picture up. Because Alexander's right, having a picture is super helpful, right? Do your best to give that a parameterization. Then let's check in before anything else happens. I don't get too crazy with the parameterization. Give you a hint. Make the first component T. general thing here. General guidance, if you're just asked to parameterize a y equals f of x function, or that form, just let your first parameter be t, and then this gives you the formula for the second parameter. So maybe you did that, and that would have been a good move. So x comma y, just like that. What do we have for a parameter range? Where should t start? 0, and then go to where? 2. And you just look to see what t values give you these 2 points. This one was set up pretty chill. So let me stop for a second and make sure we feel okay about that. Okay, well, then your next goal is let's crank this beast out. So what I'd like you to do is turn this into an integral from a to b of just t stuff. So take a minute, use what we talked about. I'll write out some extra stuff to help you here. And this is actually, here's like one more form here. Those are of t's that I inserted there. And you still need to evaluate this on the curve. So x equals what, y equals what. That just, those x, y values just live on your curve. So you're literally plugging those guys in to that function. You want pure t's here. Check it out. Let's make sure we're rolling the same page. This is the r prime of t right here. Let's take the derivative of each component. And this turns into just a nice old polynomial. Yes, sir. Yeah. Yeah, yeah. Yeah, this is our RT. Yeah, I didn't really label it well, but yes, yes, sir. That's our
So
RT.
F times R of T is what you did on that second line down there?
So this line here. So what I'm doing here is I'm taking the vector field
Yeah.
and restricting it to my curve. So I'm replacing the x with the t. So x equals t, and then the y equals 1/4 t squared. And I'm just
Right.
filling those in there, and then here doing the derivatives
The derivatives
of the parameterization.
Yeah,
So
the
yeah,
actual
so
values.
x is,
So,
Yeah, go ahead.
I see that you put the swap things out.
Mhm.
Could you explain what that's doing? again?
yes, sir. Yeah, so here, I took 2 times the X formula from RFT,
Yeah, I see that.
and then plus the Y,
Right.
comma, and you're cool with this?
Yeah, I understand how you got that, like.
Okay.
I'm just curious of what it was doing in terms of the line.
This is restricting the vector field equation to the line. So this can now give me the vector at any point along this
That
line,
line.
just by knowing the t value. I'll get the vector. I don't know if that's what you're asking.
No, it is, no, it definitely is, I just,
So this, maybe if I write a little bit of notation here, Alex, this is the vector field evaluated on the curve.
oh. It's F of R of T.
Yes. So it's this formula up here, completely with X and Y values only coming from the
F
curve.
of R of T, F evaluated R of T. That
Yes,
makes
sir.
sense.
Does that help?
Yeah, it does.
Okay, cool. Any other questions on getting this set up? You'll definitely have to do one of these. I'll keep cranking here, just because maybe this actually, I want to simplify it a little bit. What is that, 5/4, that's 3/4. And good Lord, what did I write there?
118.
Thank you. Thank you. Cubed. And now it's just Calc 1 kind of stuff. Ooh, that's nice. That's less nice. At least it's nice powers of 2. And there's a 0, so we're gonna get 4 plus 2. Oh, yes, thank you. Yep, yes, sir. Thank you. Good call. I didn't copy the minus down properly. So then that's 4. 8 divided by 4 is 2. That is 16/24. Subtracting that off. And then, who cares what this is, really? But let's go ahead and finish it. Oh, gosh. Now I'm really wishing I hadn't gone and finished it, but I think that's just minus 2/3. So yeah, so it's 16/3, whatever that means. Must mean we're mostly working with the vector field as we move through it. Is there any questions on doing this? It's tedious, but do you think you could do this? Especially if you went back and watched the recording or just looked at whatever. Okay. So let's actually notice something about this F here. This F is actually the gradient of some function of 2 variables. And that is something very special, and it makes our lives so good. So let's put a little note here. Note. This F, and I'll tell you how I know that in just a minute. This F is the gradient of some function f of x, y. Let's just note that, and we'll come back to that. But let's, and you probably can't see that. I know how to look for that. I didn't realize that when I grabbed this example that this actually had that property, but it does. So let's think about what that would mean and how am I discerning it? And then what does that get us? Well, first off, let's talk about what it gets us and then talk about how to identify it. So, why is this awesome? Oh my God. Why is this awesome? Exclamation point. Probably just a question mark. It's a little too early to get that excited about it. But we got it there anyway. So let's assume that our vector field f is equal to the gradient of some other function, little f. Remember what that means? So that means in 2D that this is the partial of f with respect to x, partial with respect to y, or in 3D, I have like that. Does that sound vaguely familiar? I hope that's not like news or anything. Yeah? Good shit. Well, if that is the case, then when I go over to look at the line integral, so then the integral from A to B of f dr, and let's set up our function r. So let's say r of t equals, and we'll just do this in 2D to make life easy. T goes from A to B, and I've got an x function and a y function here. So when I come down and look at this, this looks like this. And so now this is actually gradient of f dot dr, and that is partial of f with respect to x evaluated in r of t, comma, partial of f with respect to y evaluated on the curve, dotted with the derivative of this curve. So let's just put r prime of t there, like that. And then let's do a little bit more work here. This is integral from A to B. Now I'm going to do, I'm going to write this guy out. I guess I actually am. So this is f with respect to x at r of t, f with respect to y at r of t. Now this seems like kind of tedious, but we're getting to something that's going to pay off really big for us. And then this would be x prime of t, y prime of t, dt. And I got one more move before we see something that's happening here. This is then integral from A to B. Let's do the dot product. I'm going to write this in partial notation. So this is partial of f with respect to x, evaluated at my x of t, y of t. Now I'm plugging all that in, times x, the derivative of x with respect to t, plus partial of this with respect to y, evaluated in x of t, y of t, times y prime of t, dt. So I'm just writing that all out. Okay, now look at this thing inside here. This is the chain rule on a function f. So I've got a function f that depends on an x and a y, and then each of these depends on a t. So if I said to you, find the partial of f with respect to t, what would you do? You would say, okay, well that's partial of f with respect to x times partial of f with x with respect to t, plus partial of f with respect to y times partial of y, or derivative of y with respect to t. Do you see how this is the chain rule here?
Partial of f with respect to t.
Yes. Yeah. What did I say?
You said partial, then you corrected yourself to derivative.
Yeah. Well, so when you only have one independent variable, you can just call it a normal. Yeah. But this is the chain rule right here. This is the partial with respect to, or the derivative with respect to t of f of x of t, y of t. So let's write out what that is. Now this is cool, because this is the integral from A to B of the derivative of this function dt. This looks good, because what important calculus result?
Integral of the derivative cancel.
Yeah. integral of a derivative.
Yeah.
Integrals undo derivatives, and derivatives undo integrals. This is fundamental theorem of calculus part something, 1 or 2. So this says, oh, what's the antiderivative of the derivative? Well, it's just the thing itself. So this is f of this thing, just leave all that alone, evaluated from A to B, and so check out what we get. F evaluated at the right endpoint minus F evaluated at the left
We're
endpoint.
still evaluating, you just don't like integrate it before we evaluate it?
So yes,
So I
we
guess
do.
you are integrating it, then you're taking the derivative of the.
Exactly.
And
Yes.
then evaluating.
100%. Yes, sir. So this right here is the big result that I wanted to show you. That if, so look, the summary here is, if my vector field is the gradient of some little f, then to evaluate the line integral, all I need is f at the end point minus f at the start point. So this is equal to, let's just write this out kind of in a heuristic way, f evaluated at the end minus f evaluated at the start of path. And this f is the thing that the gradient came from, where f, little f, is the potential function, is the potential for the vector field f. Okay, now that's a lot, but it makes life so simple. This is gonna make life really beautiful because I can go back to this problem here, and if this thing is the gradient of some potential f, I can rock this shit out. Look at what this says, that all that matters, it doesn't matter how I travel. All that matters is where I start and where I end. In this special case. So this is called a conservative vector field in this case. Sometimes this is literally the definition of a conservative vector field. So let's kind of write this up and then talk about how to identify that. Bless you. So in a conservative vector field, and a conservative vector field, we'll talk about how to define that. Well, actually, we can just say it this way, i.e., a vector field that is the gradient of some potential function. Little f. So if I can go to this thing and go, oh my God, that's just the gradient of this, and I can identify this, then I've got a conservative vector field. So in a conservative vector field, line integrals only depend upon the value of the potential at the end points. Bless you. Some. So how do I know when I have a conservative vector field? Well, let's get to that, and then we can rock some stuff out. How to ID a conservative vector field. So I'm going to start in the 2D case and show you kind of the cheesy route. And then we're going to talk about it in 3D, where I'll actually introduce curl, as Brandon mentioned. You mentioned that, right? Yeah. We'll talk about the curl of a field, and that's another way to identify a conservative vector field. So how do we do this? Well, we want to see if we can find, and let's just do 2 dimensions for now, an f of xy so that our field looks like this. I want to be able to find some function whose first partial looks like the first component here, and second partial looks like the component here. Well, we know that if these functions are partials coming from some big f, that the mixed partials should be equal if things are nice, and things are always going to be nice. You really have to try hard to make that not happen. You can, but it's like it's stupid. You'll never run across it in your entire career. It's not stupid, it's just a little phony, a little bit phony. So we know this. So what we're going to do, and that is, so we check this relationship. In other words, I'm going to assume that this is partial with respect to x, and this is partial with respect to y. Let's call this f1. Let's call this f2. And I'm going to check to see, is the partial of this with respect to y the partial of this with respect to x? Wow, Daniel, sorry about that. Good. So we check this relationship by checking, is the partial of f1 with respect to y equal to the partial of f2 with respect to x? I put a little question mark there. I'm going to check that. So I'm going to take the derivative of this thing with respect to y, derivative of this thing with respect to x, and if they're the same, that means this must be the partial with respect to x of something, and this is the partial with respect to y of that same thing. So if so, then we have a conservative field. And so now we're going to come up with an algorithm. Once we have a conservative field, let's leave that guy out. Here's how we can find the potential. All right, I'll go to blue, fine. So once we know we have a conservative field, F. To find the potential, one, we're going to set big F, the potential, equal to the integral with respect to x of the first component f1. So I'm going to take this thing here and integrate it with respect to x. It's supposed to be the derivative of something with respect to x. So by integrating this with respect to x, I should get back to something close to the potential. So I take the f1 component and I integrate that with respect to x, but I need to tack on a constant. And I could potentially have here some constant that depends purely on y. Think about it then. If I took the derivative of this with respect to x, this wouldn't show up. But I want the most general thing here, so don't forget to put that on there. So we set that, we evaluate this integral, whatever it turns out to be. 2, take the partial with respect to y of the result from 1, bless you, and compare to f2. This will help us identify g of y. To identify g prime of y, because you're going to take the partial of that, integrate g prime of y with respect to y to get g. I'll call this step 3. And then step 4 is write your final answer. And this is going to make way more sense when we do it, so just bear with me. Integrate this, And then potential is equal to, we usually call it F, but it is that thing that I came up with in step 1 plus this thing that I cranked out in step 3. And you don't need to tack on like a general plus C. We don't worry about that with our potentials. All right, let's do this. So you can see how this works. I'm going to do it with that guy right up there, because that thing is conservative. Let me stop for a second. I feel like I'm just cruising. Everybody with me? We're okay? Okay, awesome. All righty, so let's take this guy here. Check. Does F1 partial with respect to y equal partial with respect to x of the second component? Look how it's mixed. So I'm going to take partial of this with respect to y. So that's partial with respect to y of 2x plus y. I like putting that question mark there because I don't know this yet. I'm not claiming that. Is that the partial with respect to x of x minus y? And is that true? What's the partial of this with respect to y? 1. Partial of this with respect to x? 1. So get 1 equals 1. True. So F is conservative. Now I'm going to figure out what is it the gradient of. So let's put that F is conservative, i.e. it is the gradient of some f, some little f. So now we're going to find little f. I'm going to go through my plan here. Step 1, I'm going to set little f of xy equal to the integral with respect to x of the first component. And I'm going to tack on this g of y. I have to actually write that in. See, then if I took the derivative of this with respect to x, this goes to 0. So I'm just trying to emphasize that multiple times. All right, partial of this, or it's kind of like a partial integral. So this goes to x squared. Where does the y go? Yes, did I hear yx? I think I did. Was that correct? Yeah. I've gotten very good at catching your barely audible answers, but that was a hell of a good answer. Plus g of y. So this is our guess at what the potential must look like. It's definitely got this and this. We're going to figure out if there's some piece here that doesn't show up yet. So then step 2 is now I take the partial of this with respect to y. So partial with respect to y of this f is 0 plus x plus g prime of y. And I'm going to compare that to the actual f2. So compare to the x minus y. And you see now I can tell exactly what g prime has to be. What does g prime have to be? Yes, exactly. So this tells me that g prime of y equals minus y. If this thing had come out to needing an x in it, then I've screwed up. At this point, this thing here needs to depend purely on y. And if it doesn't, I either miscategorize this as conservative or I screwed up some math somewhere. So that's g prime of y. Now step 3 is I'm just going to integrate that thing. So g of y equals minus 1/2 y squared. And you could tack on a plus c, but don't worry about it. And my final answer is now taking this and plugging it back into here. So putting these two together is going to give me my potential is x squared plus xy minus 1/2 y squared. Let me stop for a second. Might have to talk a little bit. Wednesday, but I won't talk long about this. Let me give you a minute to check on that, mostly because I have to pee really bad. I'm trying to cut down on my tea consumption throughout the day. Not doing a great job. Okay. Alright, give everybody some phone time, that's good. We're ready to knock this sucker out. So now, we've got our potential. I just have to know where my path starts and ends, and I can evaluate the line in. Let's go back to our curve, C. Now, to find integral FDR with that curve C. Let me see, what was that curve C? It went from where? 0, 0 to, what was the other point? 2, 1? 2, 1. So there's 2, 1. Now what we're saying here is that it doesn't matter how I travel from here to there. The answer only depends on the endpoints. So this integral is the same as if I just went straight across, which is just insane, just really wild. But this is the way it works out. This is the math of it all. You know, if you want to, if this is frustrating, get mad at calculus more than anything. So our endpoint was 2, 1. Our start point was 0, 0. And so this integral is equal to the potential f at 2, 1 minus f at 0, 0. 0, 0 is easy, just a 0, so that's cool. So f at 2, 1, I just gotta plug in there now. That's gonna be 2 squared plus x times y plus 1/2 y squared. I'm starting to be like, is this even the answer we got before? Oh wait, what was y? Y is 1, sorry, so 1 squared. So that is 6.5. Yeah, 6.5. What was our other answer?
16 thirds.
How much?
16 thirds.
16 thirds?
I think so, right?
It's like 5 and 1/3.
I must have fucked that up. Really? We got, how much did we got? 5 1/3?
Yeah, we got 5
The other way? Cormac, what do you see? You catching something?
No, well, I thought it was supposed to be minus 1/2
Oh,
y squared,
that's right.
but that still doesn't.
It doesn't get us there. Oh, right, that's right. That makes things maybe worse, just as bad.
A little
So it
closer.
was minus a half.
6, 5, 1/3.
You're fine.
We
Yeah.
can round one.
I'm just kidding. Huh. So what do I get here? This is close to it though, isn't it? This is like 5.5. But that's not good. It shouldn't be close. It should be exact. Do you see anything wrong in my last bit of? Oh, thank you. Yeah, Kayla.
I don't know if this is right or not, but when we were taking the integral at the very end, you had like -1/8 t to the third.
Yes.
And then when we integrated that, we said -1/24, but wouldn't that be 8 times 4, not 8 times 2?
32.
So it'd be
Yes.
1/32 instead of 1/24.
Yes, that's it. And does that?
I didn't do the
Yeah, I
math
think
from there,
that's
but-
it. That's probably it. That's probably
Let's
it.
just
So,
pretend that it is. So you-
what's that?
Let's pretend that it is.
Absolutely.
And then we don't have to work through it again.
I think
It's
that
one
Taylor.
over 32, it does work.
With 132, it does work.
Yeah, because it'd be 16/32.
Yes. Okay. So I screwed up a little in the first one. What you can see here is that this is way less error prone. Your calculus doesn't have to be as good. You don't have as much work to do. There's less chance of error. So we did get the same answer, but it was painful. We checked our work, and our work was wrong. Let's see, what time is it? I wanna do some work with this. No, that is not a pun at all. But I want to talk about what it means in 3D to be conservative, so we can at least tie that up. And then you can see how the thing that we're checking for conservatism here actually extends into the 3D definition. So let's just talk really quick about this thing that I didn't think we'd get to, but I'm stoked that we did. It's called curl. So given a 3D, this has to be, it kind of has to be 3D. You can go to 2D, and we're going to by cheesing it out, but it's defined for 3D vector fields. So I've got f of x, y, z, and then that's got 3 components, f1, f2, and f3. And each one of those depends upon x, y, and z. It just would be gross to have to write it all out, at least under duress. And I'm moderately under duress because I'm putting on a math show. So. The curl of F is essentially like how rotational the vector field is. So this is a measure of how rotational the vector field is. And let me say more about that. In other words, if you took at some point and you put a little paddle wheel, so that's not an X, that's a little paddle wheel. That if this thing is turned by the vector field, then there's a non-zero curl. So curl means that this little paddle, if I put it in different places, and it could change depending on where I'm at, but if this thing rotates in the vector field, then I have curl. We'll talk about how to measure it in a minute. This would be negative curl. Negative curl is clockwise. Counterclockwise is positive curl. And if curl is 0, there is literally no rotation. Yes, sir?
Are you saying like the vector direction of the vector like turns the wheel, or what do you mean by that if it rotates, that there's curl? If the vector rotates-
So yeah, so for example, if I had this vector field, I kind of saw somebody like this.
Yeah.
There's clear rotation going on there. And think about it, especially if I had higher magnitude stuff out here. Let's say I put a little paddle wheel right here.
Yeah.
So because these outer forces are greater than the inner forces, you're gonna get this rotation on this thing. It's gonna make it spin.
Yeah, so like the vector field is like, feels like a gravitational field, it would be, or it's any sort of force.
Any sort of
would
force,
be
yes.
turning the paddle.
Yeah, it's easier to think of it in terms of currents, at least when I'm trying to
Right,
understand what
like
curl
powers.
is, yeah. But if I had something like this, where everything was all uniform, no curl there. Put your little paddle wheel in there, it's not moving. So that would have no curl. Let's talk about what is curl. How do you define it? Because the definition isn't going to help you, but it's going to help you compute it.
Is there any notation for it?
Yes, Yes. Really, it's just actually the word curl of the vector field. So we define officially the curl of the vector field F, as I've defined it right here, is the determinant. Let's write out the nice notation. This is nice notation here. It is this operator, so this is the gradient operator, crossed with the vector field itself. So it's a cross product. Now that's weird, because this isn't a vector, this is an operator. So this guy right here is the vector, partial with respect to x, partial with respect to y, partial with respect to z. So it's a thing that makes new things, it's not a thing on its own. It eats vectors and spits out partials. So what does this mean? Well, cross product we did like this, ijk, and then here I'm going to put partial with respect to x, partial with respect to y, partial with respect to z, and then here's the components of the vector field. And that's the best way to write it out. Everything else is just gross expansions of this determinant, which don't really help us. This is what I remember, and that this is this, or don't remember anything and just look it on paper, and you're fine that way too, because there's no noteless exams or anything like that coming up in here. So now let's just really quickly, what if my third component is 0? So if my vector field looks like this, it's going to be partial, let's see, so I just got an F1 and an F2 and then a 0 here. So this is like 2D. I'm just killing off the third component, and these guys only depend on x and y. So in 2D, this is what my vector field looks like. And you can imagine it all happening in the xy plane, no z components at all. Well, let's think about what this would look like. Then the curl of that F is going to equal, well, we've got our definition. Let's go ahead and write this out again, ijk. And I can fill in some different things here. So partial with respect to x, partial with respect to y, partial with respect to z. Anytime I do this thing to something, I get 0 because there are no z's up there. So the partial of anything here with respect to z is going to be 0. F3 itself is 0. So I've just got F1 and F2. That makes this a little easier to crank out. Let's crank it out. So I'm going to expand first, the I. So I'm going to do the I row, first column. Is there a question? Go good? Yes, exactly. Because what I'm going to get is this little subdeterminant here. And this is saying take the partial of F2 with respect to z. That is 0. And the partial of anything that's 0 with respect to anything is 0. So I just get a 0 I out of here. And then I've got minus, I'm going to kill off that middle row and that middle column, top row. And again, I'm going to get partial of z of F1, and that's just 0, because that doesn't depend on z. And then partial of 0 is 0. Yeah, so is that all making sense? Yes, I will have yeah, absolutely. So for the z component, kill off this stuff, I'm going to get partial of F2 with respect to x minus partial of F1 with respect to y. And then that's my k component. So I've just got this piece right here. Well, okay, so this is officially the curl in 2D. What's that? Yes, sir.
Are you taking the partial of that one with respect to x, or are you already having the partial of, sorry. So
No, it's okay. I think I know what you're asking, but
you're not taking the partial first and then multiplying it by f1?
correct. Yeah, so this just means take the partial of this with respect to
No,
y.
that's definitely what that means. It just means when you have any cross product form, it seemed like you already had the partial, and you would be multiplying it by f1.
Yeah, this, I think, yes, this is just like this is a notational device, and this isn't like a critter that's a real vector. It's just what Taylor was
Gotcha.
saying, it just like, it's a way to remember how to crank out this piece.
I gotcha.
Yeah?
Uh-huh.
Okay. And then when we have this in 2D, notice how this is a vector that points orthogonal to the plane, right? If this is the XY plane, K vector points straight up. But the way this is treated in physics and wherever else this shit goes on is we just treat this as a scalar. So we forget about the K, and so you treat it in 2D, treat as a scalar. And the scalar is just this quantity, partial with respect to x of f2 minus partial with respect to y of f1. So that's the curl in 2D, that's the curl in 3D. And what the hell does that have to do with any of this? Rotational vector fields are not conservative. So a field can be classified as conservative if the curl is 0. So we have a new definition here that, let's put a little star here. F is conservative if the curl is 0. It's a non-rotational vector field. So for this, that's a very complicated thing. What about this? Let's just talk about how does this tie up with, let me just check on my time. Yeah, I'll say this. I got a little bit more I want to do on Wednesday, so I'm glad we're still meeting. Your mileage may vary on that. But remember how we said that this thing had to be the gradient of something to be conservative? So in other words, we were saying our vector field looked like this. And this was F1. And this was F2. And we said it was conservative if the partial of this with respect to y equaled the partial of this with respect to x. Well, if this thing is 0 right here, that's saying the same thing. So the curl is 0 is the same thing that we said up front. It's just a lot fancier sounding. So this thing here is partial with respect to y, right? Up there, y is partial with respect to y. And F1 is partial with respect to x. And if these mixed partials are equal, this certainly will be 0. So I just wanted to tie that back together for you. That kind of naive definition of conservative along with this more official level one here. I want to do one last example really quick. And I've got time. So I want to go back to the gravity thing. I want to at least show you how kind of cool this is, and at least an example that helped me feel like, okay, I kind of understand work, kind of. So let's say my vector field looks like this. It's just f of xy, we'll do it in 2D, and it's just 0, minus 1 everywhere. So this is a vector field, but like the very first one I drew that represented gravity. So if this is the x-axis and this is the y-axis, no matter where I'm at, I've got a constant vector pointing straight down. This is kind of like gravity. This is a little bit like gravity, right? We'll assume gravity's constant-ish over small regions. So this is gravity-esque vector field pointing straight toward the ground. And then I'm going to take that remote control and I'm going to start it here and I'm going to do all sorts of weird stuff with it and it's going to end up here. So this is my path that I traveled through there. I'm going to call that R of t. And it's some curve C. It moves in this direction. It's oriented. And we'll say t goes from A to B. So this guy is R of A, and this guy is R of B. Let's figure out what the work is. What does the work look like for moving through this constant gravitational field pointing downward? So let's Let's go. First off, conservative. Yeah, there ain't any freaking variables in there, right? Like, so partial with respect to x is 0, partial with respect to y is 0. This thing's hella conservative, so I don't have to worry about that. Ain't nothing spinning in this field right here. So let's look at the total work. It's the integral over this curve of f dot dr. F is easy. We can actually crank this whole thing out here. So this is going to be integral from a to b. F is just this dude. And then dr is going to be, let's say, we need some parameters here. X of t comma y of t. I need those to grasp onto. So this is x prime comma y prime. That's just dr. Right there. And then we'll crank this through. So this is integral a to b. I'm almost done. Notice how the horizontal component does not play a role at all. All I've got is 0 minus this thing. So it's like the y velocity on my motion of my particle or with my remote control. And hey, fundamental theorem of calculus much? We've got the integral of a derivative. So this is literally minus y of t from a to b. And so look what we get. This is minus y of b plus y of a. It doesn't care how I traveled. All it cares about is the y coordinate at the end and the x coordinate at the end. So this is just the delta y of my motion. It doesn't care about anything else. It's literally what was the change in height. That's it, and that was my total work done. Yes, sir?
So the delta like represents.
Just the change, and I was being a little abusive with that. This is just the change in height. That's all I was actually trying to say there. Does that make sense? Cool. And so if y of a is bigger than y of b, that means I started out higher than I ended, and that gives me positive work because I'm moving. It's so weird, but that's positive work, right? I'm doing positive work right now. And then if they're reversed, I got negative work. All righty, my friend. We're gonna do friends, plural, not just one of you, but you as a collective, you are one friend. I'll see you on Wednesday, and I'll hand out your final skills checks, which you can do on your own time. Got a few more things to say to you. Do you mind, Cormac, hitting the button?